So this is Dr. Shankaraiah, Department of Physics, Associate Professor. So in the last presentation, I have discussed about Module 3 of Applied Physics, which is lasers and fiber optics. So in that, in lasers and fiber optics, I have discussed about lasing action and the process that occur when light interacts with matter. And today I am going to discuss about types of lasers. And in types of lasers, basically I will discuss about ruby laser and helium neon laser. So lasers are divided into different types basing on different considerations. We divide them here on the basis of material used. So what kind of material we are using to fabricate the laser, based on that material we are classifying these lasers into different types. Okay, so here there are three different types of lasers based on the material which we use to fabricate the laser. So first one is solid state lasers. So here we are saying solid state lasers. So the material which we are using is basically solid material, solid state material. So that is why we are saying these lasers as solid state lasers. So the examples in solid state lasers is ruby laser, neodymium ag laser. In solid state lasers, we discuss about ruby laser. So the second one is gas lasers. So gas lasers. So it is clear that we use gases to fabricate these lasers. So in gas lasers, we discuss about helium neon laser. Though there are different types of laser. For example, carbon dioxide laser is also a gas laser. So third one is semiconductor diode lasers. So as the name says, we use semiconductors to fabricate these lasers. So these are semiconductor diode lasers, for example, gallium arsenide laser, indium phosphide laser, and so on and so forth. But as for the syllabus, we discuss ruby laser, which is a solid state laser, and helium neon laser, which is a gas laser. Most lasers emit light in the red or infrared regions. Okay? So lasers work in continuous mode or in a pulsar mode. So whatever lasers we are using, we are discussing about, all those lasers emit the light. You know that laser is a light amplification by stimulated emission of radiation. So we are going to say that there is a light that is coming out as a output, which we discussed in lasing action. So the light that is emitted by lasers is mostly in red or infrared regions, and the light that comes out from these different types of lasers can be either continuous mode laser or a pulsar mode laser. Okay, so first we'll start with the solid state laser, which is a ruby laser. So ruby laser belongs to the class of solid state lasers, and ruby is basically Al2O3 crystal, aluminum oxide crystal containing about 0.05% of chromium atoms. Okay, so as we discussed in lasing action, right? So in lasing action, to obtain the lasing action, what we need is a optical resonator or optical cavity. So optical resonator or optical cavity is nothing but you have an active medium here, active medium, and you have two mirrors on both sides of this active medium. So this is the front mirror. So front mirror is partially reflecting mirror. So this is partially reflecting mirror, and the back mirror is 100% reflecting mirror. So this is 100% reflecting mirror, and this totally is called as optical resonator and optical cavity or optical cavity. And this active medium is basically connected to a pump, so that we can excite the atoms from the ground state to excited state. Okay, I will discuss all this in detail again. Okay, so this is called optical resonator or optical cavity. Optical resonator or optical cavity. Okay, so it's very important device which we need to obtain the lasing action or output laser, right? So optical resonator or optical cavity contains two mirrors, and out of them the front one is partially reflecting mirror and the back one is 100% reflecting mirror, and in between these two mirrors there is active medium. Okay, and this active medium is connected to a pump. Okay, so we know that this pumping technique we use to excite the atoms from the ground state to excited state, so that N2 is greater than N1, and that is nothing but the population inversion. So to achieve population inversion, we need to supply energy, because in general the atoms will be in the ground state, so number of atoms in the ground state are more compared to the number of atoms in the excited state. So that is N1 greater than N2. So this is normal state or equilibrium state. So this is a normal state, and you don't achieve population inversion when the system is in a normal state. So what do you need? You need is a population inversion state where N2 is greater than N1, and this is called inverted state. Inverted state. Okay. So to achieve this population inversion or inverted state, we are going to connect this active medium to a pump. So using this pump, we are going to supply energy to the system active medium, so that the atoms will excite from the ground state to excited state, and then N2 greater than N1 will be achieved. That is, population inversion is achieved. So active medium is nothing but host medium plus active centers. Active center. Why do we need active centers? Active centers are important because to achieve population inversion, we need a metastable state, special state which is called as metastable state. Why do we need metastable state? Because the normal excited state, in normal excited state, the lifetime is 1 nanosecond. Once the atoms are excited from ground state to a normal excited state, the atoms will stay for 1 nanosecond, and immediately they will decay to the ground state. So it is very difficult. It is impossible to obtain the population inversion between a ground state and a normal excited state. So that is the reason why we need a special state called metastable state, where the lifetime of atoms is more compared to the normal excited state. Okay, so to obtain the, so how do we get this metastable state? You cannot, so to get this metastable state, we are adding impurities or defects to the host medium. Okay, so that is the reason why active medium is nothing but host material plus added impurities. These impurities are added to obtain metastable state. We need metastable state because we want to achieve the population inversion. Okay, fine. So that is the reason why in Ruby laser you have a host medium Al2O3 host material aluminum oxide crystal, and then this crystal doesn't have a metastable state. So it has normal excited state, but if you have a normal excited state, you don't get a population, you don't achieve population inversion. That is the reason why we are adding active centers are impurities which are chromium atoms. So 0.05% of chromium atoms. So these chromium atoms are the actual active centers. That means these chromium atoms provide us the metastable state to achieve population inversion. So ruby rod is taken in the form of cylindrical rod of about 4 centimeters in length and 1 centimeter in diameter. So this ruby crystal Al2O3 ruby crystal it's taken in the form of a rod, and then the length of this ruby rod is around 4 centimeters and the diameter is around 1 centimeter. Okay, its ends are polished such that the end faces are exactly parallel and are also perpendicular to the axis of the rod. So why we are taking the ruby crystal in the form of rod around 4 centimeter in length and 1 centimeter in diameter, and we are saying that its ends are polished. Okay, so we are taking this and we are polishing the end faces so that we obtain a optical resonator. We need optical cavity or optical resonator to for this lasing action. So to get this optical resonator, we are taking the ruby crystal in the form of rod around 4 centimeter length, and then we are polishing the ends, both ends of this ruby crystal and rod, so that we obtain this optical resonator. Okay, and the ends are polished such that the end faces are exactly parallel and are also perpendicular to the axis of the rod. So if you have, so I am taking a ruby rod in the ruby rod, and it is 4 centimeters in length and 1 centimeter in diameter. So I have polished these two faces, end faces are polished such that It is perpendicular to the axis of the rod. So these faces are perpendicular to the axis of, so this is the axis of the rod, and these two faces are perpendicular to the axis of the rod. Now these two end faces are polished such that they will act as mirrors, and in between them we have this Al2O3 plus 0.05% of chromium atoms. So this is actually active medium. So you have an active medium, and these active medium is this ruby rod added chromium atoms, and the ends of these ruby rods are polished such that you have a optical resonator. Okay, the end faces of the ruby rod are silvered so that they form the optical resonator. Fine. The rear face is made totally reflecting, and while the front face is made partially reflecting. So this one is 100% reflecting, and this one is partially reflecting. So these faces are silver such that they are going to act as a optical resonator. Okay, so we have looked at the construction. So basically this is all construction. Okay, so you can write this is construction of ruby laser. Okay, so we have looked at the construction of ruby laser, where we are taking Al2O3 crystal and we are adding 0.05% of chromium atoms, so that we have active medium which is host medium plus active center. So a host medium is Al2O3 crystal plus active centers of chromium atoms. And it is clear to us now that we are taking active chromium atoms which are impurities, because they are going to provide us metastable state. Very good. So and then we have taken this, once we have this ruby rod, we have taken this ruby crystal in the form of a rod around 4 centimeters in length and 1 centimeter in diameter, and then we have polished the end faces such that it is good. They are going to form optical resonator. Yes. So this is what we are discussing. So we have a ruby rod in the around 4 centimeter in length, 1 centimeter in diameter, and then we have polished and silvered the end so that it they act as mirrors. Front mirror is partially reflecting and end mirror is 100% reflecting, and in between then we have the ruby rod with 0.05% of chromium atoms. Okay. So we have active medium. We have two mirrors. So then this active medium must be connected to a pump, so to obtain the complete optical resonator optical cavity. So that here we are taking the pump as a xenon flash lamp. Okay, so this helical structure is a xenon flash lamp. So we are wounding this xenon flash lamp around this ruby rod, and we are going to connect this xenon flash lamp to a power supply, so that when we switch on the power, the xenon flash lamp is going to provide energy to this active system. So then there will be a pumping mechanism where the atoms will be excited from the ground state to the excited state. Okay, so that is the construction of the ruby laser, right? So here the mirrors are provided by the end faces of the ruby rod, which are polished and silvered, and one of them is going to act as partially reflecting and one of them is going to act as 100% reflecting, and we need to make sure that the front one is partially reflecting and one back one is 100% reflecting. And to get the pumping mechanism, we have taken a xenon flash lamp. Then this helical xenon flash lamp is wounded around this ruby rod, and that is connected to a power supply. Okay, very good. So this is the energy level structure of chromium atom. So this chromium atom has ground state E1 and E2 is a metastable state, and E3 prime are normal excited state. Okay, so yeah, so chromium ions, yeah, so let me see, yeah, so that is the construction. And coming to the working, how this ruby laser works. Coming to this working mechanism, the energy level of chromium ions in the crystal lattice are shown in so in figure. The energy level structure of chromium ions is characterized by two absorption bands and one metastable state. Okay, so E3 prime, these two are normal excited state and these are absorption bands, and you have a metastable state which is E2, and there is a ground state which is E1. Okay, so this is the energy level structure of chromium atoms which we have added as active centers. Okay, now. So how we are going to get a laser from this system? Right. Okay, so the working mechanism: when the xenon flash lamp is switched on, when this helical xenon flash lamp, which is connected to a power supply, when it is switched on, the discharge generates an intense burst of white light lasting for a few milliseconds. So when we switch on the xenon flash lamp, the discharge generates an intense burst of white light. So the xenon flash lamp is providing white light, which lasts for few milliseconds. The chromium ions are excited to the energy bands E3 and E3 prime by the green and blue components of the white light. Okay, so first, all the chromium atoms are in the ground state E1, and there is E3 and E3 prime. Sorry, so there is E3 and E3 prime. So E3, E3 prime are normal excited states. So when we switch on the xenon flash lamp, all the atoms which are in the ground are atoms in the ground state. They are going to absorb the, because it's a xenon flash lamp is providing white light, right? So it contains all the different colors. So by absorbing green color of the white light, these chromium atoms are going to excite to these excited states, normal excited state E3 and E3 prime. So there are two absorption bands. So if they absorb green light, they are going to excite to the E3 prime. If they absorb blue light, they are going to absorb, so blue light absorbed, they are going to excite to the E3 prime. If the atoms in the ground state, chromium atoms, absorb the green light, they are going to excite to the E3. So by absorbing these blue and green components of the white light provided by the xenon flash lamp, the atoms which are in the ground state, chromium atoms which are in the ground state, they are going to excite to these E3 and E3 prime, which are absorption bonds or absorption bands or normal excited states. Okay. So the chromium ions undergo non-radiative transition from these energy levels to the energy level E2. Okay, these are, as I mentioned, these two energy levels or absorption bands are normal excited states, and we know that normal excited states, the lifetime of atom is 1 nanoseconds. So they are going to decay to the another energy level. So here the another energy there is energy level E2, E3, E3 prime are absorption bands, and there is a metastable state E2. So the atoms from E3, E3 prime, they are going to decay to the metastable state in 1 nanosecond, because the lifetime is 1 nanosecond in normal excited states. Okay, so these are undergoing non-radiative transition, and to a metastable state E2. E2 is a metastable state, we know. The lifetime is more in metastable state. So the metastable state E2 has a lifetime of approximately 1000 times more than the lifetime of E3 and E3 prime levels, because E3, E3 prime are normal excited states, and hence the lifetime is more in E2, which is a metastable state, compared to the normal excited state. So therefore, chromium ions are going to accumulate at the E2 level. So as E3, E3 prime are normal excited state, the atoms are decaying to the metastable state, and the lifetime is more in the metastable state. So the chromium atoms are going to accumulate in metastable state E2. Okay. So the metastable state E2 is the upper laser level, and while E1 is the ground level and constitute the lower laser level. That means as the chromium atoms accumulate in E2, there are more chromium atoms in E2 compared to the energy levels. Okay, so now let us draw the another structure. So this is E2 and this is E1. We know that E1 is ground state and E2 is a metastable state. So because E3, E3 prime are normal excited state, there will be more atoms that are accumulated in a metastable state compared to the ground state. Okay, so now now we are saying that as there are more number of atoms in E2, so N2 is greater than N1. So population inversion is achieved between metastable state E2 and ground state E1. So and E2 is called as upper lasing level and E1 is called lower lasing level, because we have achieved population inversion between these two levels. So population inversion is achieved between E2, which is a metastable state, and E1, which is a ground state. Okay. Now, once population inversion is achieved, let us see what happens. Once population inversion is achieved, so the upper laser level E2 will be rapidly populated as the excited state atoms, chromium atoms quickly make downward transitions from upper energy bands. When more than half of the chromium atoms are population accumulates at level, the state of population inversion is achieved between E2 and E1 levels. Okay, so the population inversion is achieved between E2 and E1 level because E2 is a metastable state and the lifetime is more, and hence we are able to achieve population inversion between metastable state and ground state. Okay. Now, once we achieve population inversion, next we are going to see the lasing action. What happens to the next step? So the first step is done. First step is a pumping. In lasing action, we have discussed there are 5 steps. Okay. So the first step is pumping. Okay, pumping is done. And the second step is population inversion. Population inversion is done. And the third step is spontaneous emission. And fourth step is amplification. And the fifth step is oscillation. So let us see how these three other later steps are obtained. Okay. Once we completed this population inversion, then a chance photon is produced. Okay, so population inversion is achieved between E2 and E1. Okay, so there are more chromium atoms in E2 compared to the ground state E. Once population inversion is achieved, a chance photon is produced when a chromium atom makes a transition from energy level E2 to E1. So once we achieve population inversion, one of the atom of chromium atom going from decaying to the ground state. So E2 is greater than E1. So when the atom decay to the ground state, the energy difference is emitted as a photon h, which is equal to E2 minus E1. The energy of the photon, emitted photon, is equal to E2 minus E1 because E2 is greater than E1. Okay. So the atom undergone a spontaneous transition from E2 to E1. Thus, this spontaneous photon stimulates another excited atom to make a downward transition. So this stimulated photon and initial photon trigger many excited atoms to emit photons. Okay. So now the second step is achieved, and the third step is also we have discussed where, because after population inversion, one of the chromium atom is going to decay to the ground state by emitting photons spontaneously. So there is a spontaneous emission. So spontaneous emission, third step is done. Okay. Once there is a spontaneous emission, we know that this is all a ruby rod and the ends are polished. So there is this first end is a partially reflecting mirror and there is a back end which is 100% reflecting mirror. Once this photon is emitted, this mirror is going to reflect this photon. So this photon is going to come back, and when it goes to this end mirror, that is also going to reflect. So it is going to come back as input photon. Okay, so the photon that is emitted in spontaneous emission is going to come as input photon. Okay, so this spontaneous photon stimulates another excited ion to make a downward transition. Now, for the stimulated emission to occur, we need a initial photon. That photon will trigger the atom which is in the metastable state to decay to the ground state. Okay, so the initial photon or the incident photon that is needed in the stimulated emission is provided by the spontaneous emission. Okay, the photon that is generated in spontaneous emission will come as the initial photon. This initial photon will trigger atoms. One photon will trigger one atom. So this atom will decay to the ground state by emitting coherent photon because this is a stimulated emission. Okay, once the atom undergoes stimulated emission from excited state metastable state E2 to the ground state, there is a coherent photon that is emitted. This coherent photon will go back again because of the mirror. These two photons will come back, and these two photons will trigger two more atoms to undergo stimulated emission. Okay, so these two more atoms will also undergo stimulated emission and emit two more photons, coherent photons. Okay. So once these coherent photons are generated, 4 coherent photons are generated, and these will come back and they will trigger 4 more atoms. So there will be many atoms that are undergoing the stimulated emission from metastable state E2 to the ground state by emitting coherent photons. We know that coherent photons are all in same phase coherent photons are emitted only in stimulated emission. So stimulated emission, there are coherent photons. Coherent photons are in the same phase. Okay. When the two photons are in the same phase, they will undergo constructive interference and amplitudes are doubled and hence intensity is increased. Okay. So the third step, spontaneous emission occurred, and after the spontaneous emission, there are coherent photons that are generated because of atoms undergoing stimulated emission. These coherent photons, which are in the same phase, undergoes constructive interference, and hence there will be amplification of light because amplitudes are doubled, and the relation between intensity and amplitude is I proportional to amplitude square. As the T is these two photons, for example, I'm taking two photons, but there are many coherent photons that are generated as there are many atoms that are undergoing stimulated emission from metastable state to ground state. Okay, so A1 is the amplitude of photon 1 and A2 is the amplitude of photon 2. When these two photons are in phase, constructive interference occurs. So total amplitude of the resultant wave is A1 plus A2. So they are doubled. If there are four photons, A1 plus A2 plus A3. So the intensity increased as there are more and more coherent photons and they are all in the same phase. So amplification of light occurs because all the photons are coherent photons. So the fourth step is also occurred because there are coherent photons that are emitted in the stimulated emission, and hence they are all in phase and they are undergoing constructive interference, and hence amplification of these photons and you get a amplification of light. Okay, so what kind of light we are going to, laser light we are going to get in this ruby laser? Okay, red photons of wavelength around 6943 angstrom traveling along the axis of the ruby rod are repeatedly reflected at the mirrors. Okay, once they undergo constructive interference, they are going to reflect at the mirrors, and once there is sufficient energy to emit, so these are the photons are going to emit that which are in red color of wavelength 6943 angstroms, and on attaining sufficient energy, the laser beam emerges out through partially reflecting mirror. The laser emission occurs in the visible region at a wavelength of 6943 angstroms, or in terms of nanometers, you can write 694.3 nanometers. Okay, so we are going to get photons, laser beam in red color, and having a wavelength around 6943 angstroms or 694.3 nanometers. Once stimulated transition commence, the metastable state gets depopulated very rapidly and the state of population inversion disappears and the lasing action ceases. Once the laser pulse comes out, the atoms undergone already for stimulated emission from a metastable state to ground state. So population inversion ceases and you don't see the laser coming out. So the laser becomes inactive once again, and when population inversion state is re-established. Now we have to re-establish the population inversion for the lasing action to occur. So therefore, the output of the laser is not a continuous wave, but occurs in the form of pulses of microsecond duration. So once we achieve this population inversion, there is spontaneous emission and followed by stimulated emission. So the atoms from metastable state E2 will decay to the ground state and decay to the ground state through stimulated emission. So the coherent photons are emitted, and all the photons that are emitted will come out as a pulse. And to have continuous laser beam, we need to pump the atoms from the ground state to the excited state. So there is a duration to achieve the population inversion. That is the reason why the output laser beam that is coming out in ruby laser is not a continuous laser beam, but we get pulse after pulse, and the duration between the pulses is around 1 microsecond. So the salient features of this ruby laser is that it uses 3-level pumping scheme. Because you have one normal excited state, you have a metastable state and ground state. So there are 3 levels. The active centers are chromium atoms, and the pumping agent here is a xenon flash lamp. You have in this laser, there is a poor efficiency and it operates in the pulsar mode. Okay, so I'm ending here with the ruby laser, and in the next presentation I will discuss about helium neon laser. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.